In this video, we're going to learn the method of undetermined coefficients. So far in our study of second-order differential equations, we've talked only about what I'll call constant coefficient differential equations. This is where the left side has only constant coefficients in front of the various terms y, y prime, and y double prime. But when we studied constant coefficients thus far, the right-hand side has always been zero, what we call homogeneous. But now I want to figure out, how do I deal if the right-hand side is not zero? If it's some other function of the independent variable, like 3e to the 2t, what do I do then? Okay, so some terminology first. I'm going to call a particular solution, y sub p for particular, to be just any solution, not the general solution, not all possible solutions, just any one that you so wish. And then I'm going to let y sub h be the general solution to the same equation if it was homogeneous. So you keep the left-hand side, but you just set the right-hand side being equal to zero, which is indeed a type of equation that we know how to solve. So y of h is the general solution, which means it has constants, and y of p is just any one particular solution. Now, I want to consider what happens if I add those two things together, the homogeneous solution plus the particular. Well, I can just plug this in. So let me take the left-hand side, and everywhere I'm going to plug in the homogeneous plus the particular solution. So two derivatives of that thing minus 2 times one derivative of that minus 3 times, just plug it in. And then what I notice that I can separate the two different sides. I can put everything with the homogeneous solution together and everything with the particular solution together. But this just looks like the left-hand side of the differential equation twice. For the homogeneous, since it's a solution to the homogeneous, we know that that portion adds up to 0. And then for the particular solves the non-homogeneous, so that portion adds up to 3e to the 2t, which of course is just 3e to the 2t. And thus, the homogeneous plus the particular, that is a solution to the non-homogeneous equation. So here's the idea. If you have a particular solution, and I have a homogeneous solution, we can add our solutions together and that still solves the non-homogeneous equation. That's another solution to the non-homogeneous equation. I can actually do the same thing with a slight twist on it. Let me imagine that there are two different particular solutions. I have a particular solution yp, and you have a particular solution, perhaps we'll call it y tilde sub p. Well then, how much can you and I disagree? I mean, we can disagree a little bit, but the difference between you and I is a solution to the homogeneous. Again, you could prove this by plugging it in and seeing that it would add up to 0. Indeed, you could plug this into the left-hand side and you'd get that adding up to 3e to the 2t minus 3e to the 2t, which would just be 0. It's a solution to the homogeneous. So you and I can disagree only by a solution to the homogeneous. So this is going to give us a methodology. Basically, we're going to find the general solution to the homogeneous. We're going to find any particular solution you wish. Doesn't have to be anything fancy, just whatever one you like. And then if you add those together, you get all the solutions. So let me show you how this is going to work. So step 1, I'm going to solve the homogeneous. This is something that we know how to do from our past, so I'll do it quickly. You would plug in e to the rt. You get the characteristic equation, you solve for the roots of that characteristic equation, and you write the general solution to the homogeneous system as c1 e to the 3t and c2 e to the minus t, because you have these two roots, 3 and minus 1. Okay, that's the old part. But now we move on to step 2, where we look particularly at the non-homogeneity, the 3e to the 2t part. So what I want to do is I want to find a solution, any solution, one solution, doesn't have to be all of them, to the non-homogeneous equation. And what I'm going to do is I'm going to do a guess. I'm going to guess that the answer looks kind of like the right-hand side, kind of like 3e to the 2t. But because this is called the method of undetermined coefficients, you might guess that my coefficient will be undetermined. So what I mean by this is, here's my guess. Instead of the 3, I put an undetermined coefficient a. But other than that, I leave the same structure. The e to the 2t is going to be the same. So my guess is that some constant a times e to the 2t. I mean, it's a guess, so let's just plug it in. Well, if I do that, then, okay, two derivatives of this is going to give 2 times 2 is 4 times a e to the 2t. Then minus 2 times 2e to the 2t, so now minus 4 times a e to the 2t. And then finally minus 3y minus 3a e to the 2t. So just a lot of e to the 2t's everywhere. Then observe, well, I have a plus 4a and a minus 4a times e to the 2t, those cancel. That leaves me with minus 3a equals to 3, and both multiplied by e to the 2t. Well, if that's the case, then A has to be equal to -1, and I have a value for it now. My particular solution is -1 times e to the 2t. This is a solution. It's not the general solution, but it is a solution. So then finally, the most important part, step number 3, how do I put them together? Well, the general solution to this is the general solution to the homogeneous plus the one solution you found to the particular. So all sorts of subscripts here, just let's remind ourselves yg means the general solution, yh the solution to the homogeneous, and yp the particular solution, aka the solution to the non-homogeneous. So in my case, I have my homogeneous, that was the c1 e to the 3t and c2 e to the minus t, and I have my particular, which was negative e to the 2t. That's my general solution. If I had initial conditions, I could plug in and evaluate the c1 and the c2. Note, by the way, that the order here matters. So you have to form your general, which was your homogeneous and your particular, and only then solve for the coefficients. I've noticed in the past students often get the homogeneous, they solve for the coefficients first and only then add for the particular. That order doesn't work out. The second observation here is just note where the constants are coming from. The constants are part of the solution to the homogeneous, but the particular is just any one particular one that works. That's why we call it a particular solution. There's no constants in the particular part. Okay. So that's the methodology. Let's do one more example. This example is almost the same as the first example. The left-hand side, the constant coefficient part, is identical. The right side is almost the same, except it's 3e to the minus t now, not 2t as it was in the previous example. Why does this matter? Well, I mean, the homogeneous hasn't changed. We can just quote that one again. But now if I look at this, you see the e to the minus t, that's the non-homogeneity. The e to the minus t is also there in the solution to the homogeneous system. So a guess of the form a constant times e to the minus t cannot work. It cannot work because e to the minus t is a homogeneous solution. That would add up to 0. So what can we do? Well, we can do a very analogous trick that we did when we had repeated roots to constant coefficients equations a little while ago. What I'm going to do is, for my yp, I'm going to guess a times t e to the minus t. Basically what I've done here is I said, well, a e to the minus t can't work, but if I multiply by one more t out the front, maybe this will work. Okay, well, it's just a guess, right? Could be good, could be bad. Let's plug it in and see. I'm going to have to step away here because this will take a little bit of writing. But what I'm going to do is I'm just going to plug in at e to the minus t everywhere there's a y. We've got a single derivative and a double derivative. This is going to involve some product rules, so I'm going to step away to give myself a little bit of space here. But if I execute those product rules, then I would get, well, this long, messy expression. You can check it if you wish. What I do want to note, though, is that if I look at all the terms that are of the form t e to the t, well, I have an a, I have a plus 2a, and then I have a minus 3a, which cancel. So those three terms all cancel. That leaves you with, well, if you count them up, minus 4a e to the minus t is equal to 3e to the minus t, which is the right-hand side. Okay, so then what does that mean? A has to be negative 3/4, and thus I can state what my general solution is. My general solution was the homogeneous plus the particular. The particular is minus 3/4 t e to the minus t. So the method is the same. Solve the homogeneous in general, and then guess just some particular one, and then add them together by our theory. The only difference was you had to be a little bit more careful about your y particular just to make sure it didn't overlap with one of the solutions for the homogeneous equation. So then we turn to the question of, what kind of guesses should you do in general? So let me put up a little bit of a chart here. So in the left column, I have different types of non-homogeneities, the things that could show up on the right-hand side of your equation a bit confusingly. So for example, you have exponentials or polynomials or sine and cosine terms. And in the right column, I've told you what you should guess for your y particular. So for instance, we saw if it was exponential, guess an exponential of the same form, a e to the rt, where a is an undetermined coefficient in the method of undetermined coefficients. If it's a sine term or if it's a cos term, well, you can guess a sine and a cos of the same frequency, like sine rt, you guess sine rt, but here's the trick. You have to have a sine of rt plus b cosine of rt, even if your left-hand side only had one of those two terms. The idea is that derivative of sine is cosine, derivative of cosine is sine. So you need to have both sines and cosines in your guess if there's any sines or cosines appearing in the non-homogeneity. And then for a degree n polynomial, like say t squared, you'd guess a degree 2 polynomial, the generic degree 2 polynomial, a0 plus a1t all the way up to an t to the n. And then there's two caveats. The first caveat is what we talked about. You might need to multiply by some t's. If the solution that you get is a matching to the homogeneous, you multiply by t or t squared or t cubed, however many multiplications of t's to a natural number, s is a natural number, you need so that the result you get is not a matching to the homogeneous. And then the final caveat being that you might have a combination of these, like the sum of them or a multiplication of them, in which case you add or multiply the guesses as well. So a final illustration of this, I won't do the algebra for it, but I'll tell you what the guess is. So same left-hand side, same homogeneous part, but the right-hand side is really messy now. T squared plus 3 to the minus t times cosine of 4t, it's a mess. So my homogeneous, we know what to do there, but what about my particular? So the particular is a bunch of things. For the t squared, that was a polynomial. So you guess a generic degree 2 polynomial. Now note, I am not guessing ct squared. I'm guessing a generic degree 2 polynomial, a plus bt plus ct squared. You got to include all the terms of less degrees than that. Then for the exponential times the cosine, we've seen that if there's a cosine term, you have to have a cosine plus a sine term. So I'll do that. A constant d times the exponential cosine of 4t, and then a constant e times the exponential times sine of 4t. You have to have both the cosine and the sine term added together with different coefficients. Final note is that if it was just e to the minus t without the cosine, you would have had to multiply by the extra value of t so you didn't match the homogeneous as I did in the previous example. But here, e to the minus t times cosine, that is not a solution to the homogeneous, and so there's no need to multiply by any extra t. So that would be my guess. Now if you plug it in, there's going to be 5 different variables, a, b, c, d, and e, and it could be quite a mess to go and evaluate them. I didn't even test to see how messy it would be in this particular case. But it would just be algebra even if it is messy. So you could in theory go and solve for the a, the b, the c, the d, and the e, and then you would know your particular. Final answer, homogeneous plus particular.